So let us see. Okay, this is much, this is more effective. So this is our obvious huge stitching artifacts. Because here during this acquisition the patient was breathing. Stitching artifacts occurs when there is breathing, when you move the probe during the acquisition, but also, and we discovered that there is another cause of stitching artifacts. If you have, if you are in a teaching hospital or you have fellows, when you make some acquisition, some of them may bend on the bed of the patients and moving the bed to try to see what you are doing. This is another way. Not always stitching artifacts are so evident. Sometimes are much more subtle. In this case, we accepted this data set because just to look at the anatomy of the mitral valve, these stitching artifacts occurring outside of the mitral valve is not a big issue. However, if we need to quantitate, this is not a good acquisition. So if you wanted to avoid them, all the discussion we had before, I can skip this one, how to detect. This is the blurring that I was talking before. This is a catheter for a mitral clip entering from the interatrial septum, and you see how thick is the catheter, and the borders are almost indistinguishable, and this is due to the point spread function. This is a near field artifact that in some cases can be mistakenly seen as a thrombus. And one way to make the differential diagnosis between the two is to use your multi-slice. And you see here that it's not a real structure, it's going away in and out, and particularly the apex is contracting normally, so it's quite unlikely that it may have a thrombus. Much more difficult to identify are these type of artifacts. This is the mitral valve seen from the ventricular perspective, papillary muscles, anterior leaflet of the mitral valve, and you have this mass here. This it seems to be a real mass, but indeed, if you look from another perspective, you realize that this mass doesn't move together with the other structures. And you see that is the so-called stationary artifacts that is due to a costal rib or something, but on the volume rendering, it seems to be a real mass. You have just to look at the image characteristics to see. There are also reverberation artifacts, and these are really tough because you may think that this is a mechanical bioprosthesis, a B-leaflet one in a mitral position, seen from the atrial perspective, and you see that it seems that one of the occluders is stuck. This only one is moving, but indeed this is not true, because if you look here, both of them are moving. This is just the reverberation due to the angulation of the incident ultrasound beam that seems that this is a stuck occluder. If I change the point of view, instead of having this angulation, but I have a real on-face view, you can notice that both of them are really opening and closing. Pay attention to this one, particularly when you have a prosthesis or the structures, otherwise you can make really big mistakes in the diagnosis. Dropout artifacts we have discussed yesterday. They, particularly when you are examining very thin structures like the aortic valve, the interatrial septum, you can see holes over here and here and here that indeed may be complications of an endocarditis, but may also be just dropout artifacts. Another structure that is very keen to have artifacts is the interatrial septum. Here you see two transthoracic data sets. We are looking at the interatrial septum. Both of them show an hole, but this one has a very well-defined margins, and it's a real interatrial septal defect. This is entering and it's coming and going away due to the fact that there is a thinning of the interatrial septum during ventricular systole with the shaggy margins that is not a true defect. In any case, when we have doubt, as we discussed yesterday, we put the color to see if there is real flow. Dropout artifact can be particularly evident. This is an interatrial septum with interatrial aneurysm. You see that it seems that there is a completely cribrous interatrial septum, but indeed of all these holes, just one is real. This is one way to look at them. If I am not sure if this one is a true interatrial septum defect or an artifact, even if with these well-defined margins I am confident enough, always have a color to having a match between the flow and the origin of the orifice. Probably I have, no, okay. These are the main artifacts that we can encounter in 3D echocardiography. Questions about that? No. Okay. If not, I think now the data set have been uploaded. Is it true? So we can go through the quantitation. Sorry, we have a lot of changes and okay, thank you. Okay, so on your computer, you should have this patient, Visentin Chiara. If not, just in the last name, type the first letter, VIS. Double click, and we have the data sets. We will take the data set number 50, the left ventricle, that we have seen before, and we will select the folder measure. In the folder measure, the subfolder volume, and from a volume we will select 4D Auto LVQ. Here we have the usual display for the orientation of the data set with the 3 views, the view that we used for the acquisition, and by default the 60-degree and the 120-degree. We cannot change the view that we have used for the acquisition, but we can optimize the derived views, the 2-chamber and the long axis, by controlling their orientation on the short axis view that you see here. We have the green axis and the white axis that control the long axis view and the 2-chamber view respectively. If you wanted to change their orientation, simply move your pointer on these lines and you can change the orientation, and you will have the change of the view in order to optimize and to obtain a true 2-chamber view and a true long axis view. Okay? Then once the views are optimized, we have to use our pointer as usual with the 2 functions of translating and tilting to make the vertical dashed line passing through the apex and more or less the center of the annulus in all 3 views, like this. Finally, even if it doesn't affect the quantitation, you can move also the blue line that controls the position of the short axis view. Are you with me? Now we can start with the end diastolic volume. And here we have 3 ways of measuring it. The default one that I am going to show, the fully automated where you don't need to do anything, and the fully manual where you need to really carefully initialize. We will see all of them because there are conditions where it's better to use one instead of the others. The most frequently used is the semi-automated that I am going to show. With this, that is the default one, what you need is just to identify the apex of the ventricle by placing the green cross on the apex in one view. You see that when you place it, a red dot appears on the other 2 views. And if you have performed a accurate orientation of the views before, these 2 red dots should be at the apex also in the other 2 views. This is the proof that you are not foreshortening any of the views. When you are ready, just click with the left button of your mouse and then identify the center of the mitral annulus, not on the leaflets, but on the mitral annulus over here. If you click, the system automatically detects the endocardium for you. Very easy, very fast. you can check the accuracy of the endocardium tracing. For example, moving the blue line. So if you are on the longitudinal axis, you can move the blue line up and down and control here the accuracy of the endocardium. You see, for example, what? If you wanted to make any correction, just go with the right button, click on the right button, then you can, click on the right button, then go and lock view. So you are freezing the motion of that, and then you can make any changes. For example, here you see that we have some black spots between the automatically identified endocardium and where I would like to have the true endocardium. I put the green cross there, and then I simply click with the left button of my mouse, and immediately the shape is re-edited for the entire contour. Why we needed to edit? Because this software is still, let me say, the old way that tries to identify the endocardium using the black and white interface. And unfortunately, due to the suboptimal spatial resolution of 3D echo, here, with trying to look at the black and white, it just detects the tips of the trabeculae, not the compacted part of the ventricle. So if we wanted to be accurate in comparison with the magnetic resonance imaging, we should go in the compacted part of the ventricle. And so being really in the white and not leaving these black spots between the endocardium and the line traced by the computer. This is why usually we go really in the white and then click like this. You will never overestimate the volumes. You will usually always underestimate compared to magnetic resonance imaging. So be generous and go always in the white. When you're ready, you can click again on the lock view and continue to check. If you move your pointer instead of the longitudinal views on the short axis, you will see that your derived plane now is a longitudinal view. You can rotate this long axis all around the contour in order to check really millimeter by millimeter the accuracy of the endocardial identification. Again, if you need to make any changes, click with the right button, lock the view, and when the view is locked, you can make any changes that you want. Is it okay? When you are ready, you go on the ESV. Once again, you click on the apex, checking that is the true apex also in the other two views. Then go in the center of the mitral annulus, and then it's done. Usually in systole, when the trabeculae are more one close to the other, the software becomes much more precise. When done, we can go on a volume waveform. Now what we have done in the end systolic frame and end diastolic frame is exported to all the frames into the data set in order to obtain the Beutel throughout the dynamic Beutel. This is a surface rendering, as we discussed this morning, a mapping of the endocardial surface in all the circumference. And this is the volume time curve of the left ventricle. Before approving, I will check that the contour is following the correct motion of the walls, and that the volume time curve is a physiological one. Emptying of the ventricle, rapid filling, diastasis, atrial kick. Are you with me? Okay. Now we can stop here and saying, okay, I will approve the images, the data, and they will be automatically exported in our reporting system. Or I wanted to have a full characterization, so I will move to the next step, that is left ventricular mass. The system starts and make another automatic identification that is of the epicardium, because the mass here is measured and not calculated anymore. And the way of measuring it is to make a subtraction of the endocardial volume from the epicardial volume to obtain the actual volume of the myocardium multiplied by 1.55, that is the specific weight of the myocardium, to provide the left ventricular mass. You see here that you have two lines, the endocardium that is gray, that cannot be changed because it's the one that we have optimized before, and the epicardium that is green, that we can edit with the usual way. If we like to have it larger or narrower, just put the green cross where you wanted to see it, and then click with the left button, and all the mesh will be updated. I told you that the green one, the gray one cannot be changed. This is not entirely true, because still I have the way to change them. If you go here, now we have the epi, but if I click on the arrows, I can have the endo, that now is green. Or if I click again, I have both of them, they are green. So both of them can be changed. But I will not recommend to use these, because when you put your cross, the system doesn't understand if you wanted to change one or the other. When done, we can move on to the 4D strain. Everybody's with me? Okay. And then we have here a change, because the system identifies the end systolic frame, and we have two masses, end diastolic and end systolic. This is not a mistake, it's just an internal control on the accuracy by which we have done the mass measurements. If the mass measurement is correct, should not be a significant change between diastole and systole, because the mass is always constant. Only with the M mode it changes. Here we have a big jump on that, so there is a problem. And the problem is the erroneous striking of the apex, obviously, that I needed to bring down. Why we have the end systolic mass? Because particularly when we have large ventricles, sometimes you cannot see adequately the epicardium when you have the end systolic volume, the large one. But when the ventricle becomes smaller, like in systole, you can see it better and trace in a better way. Here I have to correct the apical part, bringing it down. It's got crazy. I don't know why. Okay. I don't know why it is that. Okay. Okay, there is something wrong over there. However, the concept is that one. I will do for strain results in another. Do you have the same mistake in your? No, it's just mine. So I will go back in a moment. Okay, here I am. No. I don't know why, but in this computer doesn't want to have. Okay. Sorry. Go on 4D strain results that probably on your computer will work very well. It takes a few seconds because it has to measure the speckle motion frame by frame. Okay, and now we have all the strain components. That's very interesting because we have spent a few seconds, but now we have all the strain components available with just one click. This is the longitudinal strain, but as you see here are listed also the other, the circumferential one, and you just click on the one that you like to see, and this will be immediately displayed. Circumferential, radial, and you have also a new component that is the area strain. Do you have the concept of area strain? Area strain is a composed strain. It's not a linear one, but it is like this one, where we have the circumferential component and the longitudinal component. So the area strain is how the area of this square changes in the different directions during the cardiac cycle. And it's been shown that in many diseases, this is the most powerful predictor of the outcome, like in a hypertensive heart disease or in amyloidosis. Then you have also the rotation, that is the twist of the ventricle, and finally the torsion, that is the twist divided by the length of the ventricle, the true torsion. If I go back to my longitudinal strain, this is the peak longitudinal strain. That is the most similar to the 2D strain. So it's the result is an average of the peak strain of each segment, independent on the time they occur during the cardiac systole. But I have also a more physiological one, that is the dynamic peak, the dynamic that I can see only if I stop running the cardiac cycle, because changing frame by frame, I can change the strain. So I have frame by frame strain throughout the systole and the diastole. And this is different from the one before, because now is the average of the peak volume at this point in time during the cardiac cycle. And so also, if I go to the end systolic frame, as we had before, the value will be lower than the peak one, simply because the other one is the average of the maximal values at any time they occur. This is a more, let me say, physiological one. Or I can have a dynamic peak. That's another option, that at the every frame makes the average only of the peak. So you have a lot of information just taken from a single acquisition, from the apical approach. From one acquisition, we have got the volumes, we have got ejection fraction, stroke volume, cardiac output. SPE is a sphericity index, and it is the ratio between the volume of the ventricle, the actual volume of the ventricle, and the volume of a sphere whose diameter is the length of the ventricle. Then we have the mass, and we have the four components of the strain, the deformation, the rotation, and much more. This is for those who think that 3D echo is a waste of time. Imagine how many views and how many tracing you have to do to obtain all this information with conventional echocardiography, and probably we are not able to obtain them. Okay, saying that, okay, questions from you, comments? At the moment, useless, I would say. It's still not mature for clinical, and indeed we still are obtaining better results with the 2D strain. But theoretically, it's the right way, so I am confident that in the future, with the improvement into the quality of the data sets, because now the main problems are the basal segments, those who are in the far field of the ultrasound. But with improvement of the quality of the data set, this will be our future. At the moment, it's not ready.
So how useful is topographic use for when we are doing a stress echo?
The 2D strain, this bull-high display is very useful. 3D strain is not ready, as I just said. But this is to show you the various options here. Okay, if any other question about the left ventricle? If no, we can go back to the archive, always Visentin Chiara. And now we will select the data set number 55 for the right ventricle. Again, dedicated acquisition. If you wanted to have the right ventricle and the tricuspid valve, you cannot use the conventional 4-chamber for the acquisition. You need to have a dedicated right ventricular focused view the most difficult part to include in the dataset is the anterior wall of the right ventricle. So use the multi-slice display to ensure that the anterior wall of the right ventricle is in your dataset. Only if you have a good quality dataset, you will have a reliable quantitation. Then you will also always the options to reposition your slice as we have done before. But now what we are interested in is in the quantitation. So we go to measure, we go to volume, and in volume we will select 4D auto RVQ. And you should have this type of display. This is a more modern software package that looks at the speckle tracking, so it's more robust, and also shows you the icons, how you need to orient your dataset. Unfortunately, this icon is wrong. They are going to change it because it shows a true four-chamber view, while we need a dedicated right ventricular focus. But the concept is always the same. We needed to have the yellow line passing through the apex of the right ventricle and the center of the mitral, like this. Then you reposition the tricuspid at this level. When you have placed the correct longitudinal cut at this level, you should have a two-chamber view of the right ventricle in the yellow panel. Once again, rotate the green line now in order to have the green line passing through the apex and the center of the tricuspid valve. Sorry? Okay, so go to measure, volume, and in volume you have to select 4D auto RVQ. Now we have just to orient the short axis views, to rotate a little bit in order that the green broken line passes through the largest part of the crescentic shape of the right ventricle in this way. Once again, if we spend a few seconds more in this orientation of the dataset, then the next steps will be much quicker. Are you here? Okay, now we are ready. We go on set landmarks to the second step, that is the dataset initialization. And here we have to identify the tricuspid annulus at the level of right ventricular free wall. Then the hinge point of the septal leaflet of the tricuspid on the annulus. and the right ventricular apex. On the short axis view on the right, we will identify the point where the free wall of the right ventricle attaches to the interventricular septum posteriorly and anteriorly, and finally the right ventricular free wall. Again, the right ventricle is even more trabeculated than the left ventricle. So don't stay on the black and white interface, but go inside of the white, like that. Yep.
Start. In diastolic volume.
You are, no, you have selected the auto LVQ.
What?
You need to go to the auto RVQ.
Okay, okay.
Okay, then you make a proper orientation, like this. Okay, and like this. Then we rotate a little bit. Okay, here we are. And then you can go on the set landmarks and tricuspid annulus, apex, posterior hinge point, anterior hinge point, free wall, and here you are.
Oh, that's great.
Okay, this is the automatic detection of the endocardial surface that is shown on a dynamic model on the left, and diastolic frame in the center, and systolic frame on the right. I told you that here we definitely need manual editing because of the heavy trabeculation. You see that there are a lot of black spots between the green endocardium and the true white, and just go on the portion of the endocardium you wanted to change, click with the left button, and just drag the endocardium to the new position that they should have. This is very easy and user-friendly. Like this, and like this. Do it in diastole, and again in systole. Okay, like this. Why here I have a broken endocardium?
Oh, that is because of the right bottle branch.
Yep. This is right ventricular outflow tract, and there is the aorta that is crossing at this level. When the left ventricle shortens in systole, the aorta comes in your cutting plane. And so this is the right ventricular outflow tract, this is the right ventricular inflow tract that are separated. When you're ready, go to results. And now we have our Boitel. You can go on the Boitel and you can rotate it in order to have a proper anatomical representation. This one is the tricuspid valve, the right ventricular outflow tract with the pulmonary valve. This concavity is the left ventricle. And here we have the right ventricular free wall. These are the measurements that has been taken, the volumes, the ejection fraction, which is the lower level of normal right ventricular ejection fraction. 45. So it's lower than the left, and the volumes are usually larger because the right ventricle is a volume pump. Then we have the diameters taken at the base and at the mid-level, the length of the right ventricle, the TAPSE, and the fractional area change. Once again, if you wanted to see how those measurements has been taken, just click on one of them, and this will be shown into the data set. Those measurements are okay, except for the TAPSE, because the TAPSE here is not equal to the TAPSE you measure with the M mode. The TAPSE with the M mode is the motion of the tricuspid annulus as taking as a reference an external point that is your probe. Here is the shortening of the annulus taking as a reference as the apex. If the apex rotates, it changes completely the reference. So the TAPSE with the M mode cannot be compared with this shortening of the longitudinal axis. Okay? Any question on the right ventricle?
What is the normal value of TOPSy with this BD evaluation?
Oh, really, I don't know. I have never tried that. To be honest, having the ejection fraction, having the volumes, we don't look anymore at TAPSE. Okay. Saying that, we have seen yesterday the left atrium, that is the last quantitative part that we are missing. Is okay, or you wanted to see it again? You want to see it again? So, to see it again...
Sir, to edit is how to do?
yes,
to edit,
I think to edit.
Edit means to, if you feel that we have not tracked the endocardial border right.
No, this is okay. Probably I would still enlarge a little bit this one, just to
click
be
and drag
really
on.
on the white.
Okay.
And you can just, in order, in this way, because you are always underestimating, never overestimating. So this, I think, it's okay. Probably here I can move a little bit really at the annulus plane. Oh, nice. Okay. And also here.
I just know how to move that. I got it.
Yeah.
You have to drag it, click and drag.
You can drag and edit. Okay. So for the left atrium, we need number 52, I would say. Where we have a data set including both the atria. And again, to compensate for the increasing depth, we have reduced the size of the data set We don't need the free wall of the ventricle. We don't need the free wall of the right ventricle. We just need the atrium at the best temporal resolution. When we are sure that the entire atrium is included into the data set, checking with the multi-slice, we go again on measure. And this time, why I don't have the for the auto LA here? No, this is not. This is the 2D. I don't have it.
Some laptops don't have it. Some laptops.
Ah, because you needed the 203. You have? This is one is a 202. Also, this one is a 202. Okay. Can we connect the machine? Because on the machine there was the 203. You can take this Byzantine. I will show on the other one. What?
No, under the volume you should have that option. That is not. You have.
No, you should have something that is written like this one for the auto LAQ. Do you have the machine connected? No, that should be connected. Okay, perfect. One patient that has been taken, yes, one with an atrium. No, those are transophageal.
Sir wants to demonstrate that LA assessment. That is
Okay,
not included in that.
it is there in this.
Yeah. Yes, this one probably.
Sima Vinash, send it.
Yes. Okay. So we go on measurements. So in a volume, you have this auto LAQ. You click on that, and you have the usual display. First, we have to orient the data set following those icons, and then we can initialize. So using your translating and tilting options, we will have the left atrium passing through the center of the mitral annulus and the roof of the atrium. And this should be done in all three views. Like this and like this. Then we move the mitral valve in the center of the mitral annulus. And when ready, we just go to review. The walls of the left atrium are quite smooth, no trabeculations, so the software is very accurate. In any case, if you needed to change anything, it's the usual way. You go on the endocardium you wanted to change, click with the left button of your mouse, it becomes red, and you just drag the endocardium to the correct position that you wanted to set for this particular patient. Are you here? Then ready, go on results, and you have your Beutel. This is the mitral annulus. This is the roof of the atrium, and the quantitation. Not only the maximal volume of the left atrium, but also the minimum volume, the one after the P wave, the contraction, the volume before the atrial contraction, the left atrial emptying volume, and the left atrium emptying fraction. So functional, phasic function of the left atrium, and also the strain and the three components, well, the three phases of both the longitudinal strain. So longitudinal strain reservoir, longitudinal strain conduit CD, longitudinal strain CT contraction, and circumferential strain reservoir, conduit, and contraction. So very quick, very easy, and a lot of information. In the lower panel, you have, as usual, the volume time curve of the left atrium, showing the reservoir phase, the conduit phase, and finally the contraction after the P wave. So you have really a very detailed measurement of the function of the left atrium. And this software applies as well to the right atrium. Questions? Comments? Yep. Yes. Oh, thank you very much for coming. Thank you for joining. Thank you, sir. Thank you for joining.
Thank you, sir.
Thank you very much for joining. Okay, any difficulty on the left atrium? Okay, if it's the easiest, Yes, it's very simple. Okay, so we have concentrated in one morning 10 years of work that we have done in our lab. So hope that it's been, of course, it's a quick overview. You have to experience more by yourself. You can do it, and then if you have any doubt, you can write me, call, and we will try to help. That this is, hopefully, we will meet again and we can discuss cases. Also, if you want and you have the opportunity, you can try to come to Italy. Next September, we will have this 3D Eco meeting. Yeah, if they are interested. And this will be a unique opportunity to try all the eco machines in just 3 days, because each vendor will have a specific lounge where they allow you to try the software, their machine, and also to learn from the real expert around the world about their experience with the 3D Eco and the most advanced tools in that. Thank you for joining. Thank you very much. Thank you. Thank you. Ah, thank you.
1 second, sir.
I hope these photographs will be in the clinics now.
Yes, exactly. Okay.
Any questions? Shall we close or continue?
Beautiful workshop. Amazing.
Thank you. Thank you. Thank you very much. I really appreciate you have been very collaborative, and this was makes my life much easier.
I have been to Italy 3 times,
Oh,
and I'd like to be there once again, to be in your place.
come.
Padua, I think, is in between Florence and Venice.
No, it's really close to Venice. Just 20 minutes. It's in between Venice and Verona. So you can.
जो नहीं कर रहा था इसलिए पढ़ा था